This is my Arduino code for Lab 4. So in the first part of the code, we take the output from the end scope and put it to nlog pin 5, and the output from the potentiometer and read it at nlog pin 4. And then based on the potentiometer value, we can change the sampling frequency as seen in these else-if statements. And then the part of the code beneath that is basically a timer using the micros function so that we take the sample at the given frequency. Here are the plots of the signal frequency of 75 Hertz being sampled at various sampling frequencies, as we can see labeled. And of these plots, the only two that were aliased were when it's sampled at 198 Hertz and 496 Hertz. And we'll go into the calculations later. So these are the plots of a 100 Hertz signal frequency being sampled at various frequencies, as we can see labeled once again. And in this case, the 199 Hertz sampling frequency, 139 Hertz, and 99 Hertz sampling frequency all are aliased, but the 497 Hertz frequency is not aliased yet. These are the plots of the signal frequency of 215 Hertz at various sampling frequencies. And once again, the only ones that were aliased are when we sampled it at 109 Hertz, 139 Hertz, and 98 Hertz. Finally, we have the plots of a signal frequency of 300 Hertz. In this case, all four plots of sampling frequency from 97 Hertz to 497 Hertz are all aliased. So here we have our calculations of how we found the alias frequency. So in the first line, we take the frequency and divide it by the Nyquist frequency. And so in this case, I'm doing a 75 Hertz signal being sampled at 97 Hertz. As such, we find that the frequency over the Nyquist frequency is 1.546. And from that, we can go to our folding diagram. And then as we see in our folding diagram, we fold from 1.546 down to 0.4536 Nyquist frequency. Using this folded frequency, we multiply it by the Nyquist frequency to get our alias frequency. Here we can see that 0.4536 times 48.5 is 22, so our alias frequency in this case will be 22 Hertz. And based on this folding diagram interaction, I have the formula beneath it, which is the frequency over the Nyquist frequency minus the nearest even integer. And the absolute value of that times the Nyquist frequency will give you your alias frequency. Using this formula, I was able to quickly find all the theoretical alias frequencies of the different sampling rates at different signal frequencies, as we see in the next table. So this is the summary table of all the theoretical and experimental alias frequencies at the different signal and sampling frequencies. And as we can see, where all the theoretical values are very close to our experimental values, and the only ones that were kind of off were when we got to a very low alias frequency at the 100 Hertz and 300 Hertz. Even then though, the biggest discrepancy is only by 3.5 Hertz. Here is the second part of the lab of the square wave, and right now I'm adjusting the potentiometer so we can change the frequency with it. But let's examine the amplitude spectrum plot. From the amplitude spectrum plot, we see the Fourier series for a square wave. As we expect, the series is the sum of frequencies with the magnitude decaying at a rate of 1 over x, and each harmonic frequency occurs at a constant multiple of the fundamental frequency. Now we will change the wires to our analog pin from the pulse output to the analog output on the end scope in order to see our triangle wave. So similar to the square wave, we can see that there's an infinite amount of harmonic frequencies occurring at multiples of the fundamental frequency. However, the magnitude at these harmonic frequencies decreases at a much faster rate, and we can only the first 2 or 3 harmonic frequencies are visible on the plot. And this makes sense as a triangle wave is much more close in shape to a sine wave than a square wave is. As such, the harmonic frequencies do not have to play as big of a factor to make the shape of a triangle wave.